Number 1, evaluate the integral of 1 over 2x minus 2 squared from 0 to 2 with respect to x. So right off the bat, I know that this integral does not converge. And the reason for this is actually an improper integral. It might not seem like it at a first glance because there's no boundary that's infinity or something, but this is actually in fact an improper integral. And the reason I know this has everything to do with what the boundaries are and what the denominator is, considering this integrand is a fraction. And so one of the other things you have to look for when judging whether or not it's an improper integral is whether or not there's a vertical asymptote within that occurs in between the boundaries of integration. So in this case, 0 and 2. And in this case, there is a vertical asymptote that occurs between 0 and 2. And you won't realize that if you try to just evaluate this integral manually. If you do evaluate this manually, you will get an answer, but it won't be correct. And I'll show you why. So the way you can figure out that this has a asymptote that's in between these two boundaries is by finding it algebraically, or by doing by graphing the integrand and doing a visual inspection. So I'll show you how to do it the first way algebraically. And the way to do that is just to focus on this 2x minus 2 portion here and nothing else, because that's the thing that's going to have the biggest impact on what I'm getting at, that being the vertical asymptote. Because since this is a fraction and x is a variable, depending on what x is, there is a possibility that you'll end up with a scenario where this simplifies down to 0. And if this simplifies down to 0, you end up with 1 over 0, and you can't divide by 0. And so if you were to graph that, that's where the asymptote would be, wherever you end up where the 2x minus 2 portion simplifies to 0. So for that, you just take that out, set up an equation saying 2x minus 2, and set that equal to 0, and then solve for x. And when you do that, you'll find that x equals 1. So we know that there's a vertical asymptote when x equals 1. And that's in between these boundaries of 0 and 2. And then if you're not sure how to see that just by solving for x algebraically, if you graph it, it'll make more sense too. So if you were to graph this integrand, you'd end up with something, and I'll just put x and y here. If you were to graph this, you'd end up with something that looks a little something like this, where x equals 1 is here. So you can see here that these two lines, they're never going to converge on each other because we have a vertical asymptote here, like I was talking about. And the interval of integration is from 0 to 2. So that would be from the origin here to x equals 2, which is somewhere around here. So if you were to evaluate this integral manually and just do a normal computation, you'd get an answer, but it wouldn't make sense because when you look at this like an area under the curve type of question, the area is going to be infinite because these lines are never going to converge on each other. And so this region ends up having an infinite area, if that makes sense. And so as a result, this integral does not converge. Question 2. What is the area of the region bounded by y equals 4 times the tangent squared of x, y equals 0, and x equals pi over 4? So this is a question of just finding the area between two functions. And in this case, some of the things work out quite nicely. It always helps, especially when they were nice enough to give us a graph of what y equals 4 tangent squared of x is. It saves us a little bit of time in terms of figuring out what the area that we're trying to find. Because for questions like this, it always helps to, at least for me personally, I like to visualize it. And so from here, we know that y equals 4 tangent squared x looks like this, and y equals 0 just ends up being the x-axis. And then x equals pi over 4, that ends up being somewhere around here, something like this. So the area that we're trying to find is this little area that I just shaded. And so from there, we can set up our integral and also set up our boundaries. And for this, we can just integrate with respect to x. And since we know that 4 tangent squared of x equals 0 at the origin, that already sets up our lower boundary of 0, and our upper boundary ends up just being pi over 4, since we have the x equals pi over 4 here. So the integral ends up looking like the integral of 0 to pi over 4 of 4 tangent squared x dx. And we also, 4 is a constant, so we should take that out. It always helps to take the constants out of the integrand when you're integrating. So that ends up being equal to 4 times the integral of pi over 4 tangent squared x. And from here, the integral of tangent squared x can be found by using an identity. Recall that tangent squared of x plus 1 is equal to secant squared x. And so on the flip side, secant squared x minus 1 is equal to tangent squared x. So this integral ends up becoming the integral with 4 outside. Can't forget that, by the way. And from 0 to 4 of secant squared x minus 1 with respect to x. And we know that the integral of secant squared x is equal to tangent x, and the integral of 1 is just x. So this evaluates to 4 times tangent x minus x from 0 to pi over 4. And then from here, we can just plug in our boundaries. And so that ends up being 4 times the tangent of pi over 4 minus pi over 4 minus the tangent of 0. Wait, hold on. Let me remove this bracket since these are part of the same things. Minus tangent of 0 minus 0. And this just simplifies down to 0 because tangent of 0 is 0, and then 0 minus 0 is 0. And the tangent of pi over 4 is equal to 1. So you end up with, when this simplifies down, you end up with 4 times 1 minus pi over 4. And then you can distribute the 4, so you end up with 4 minus pi. And this ends up being the final area of this original region that we found here. So the answer to this problem ends up being D, 4 minus pi. Number 3, find the value of a if the integral from 1 to e to the 4th of x ln x dx is equal to a minus the integral from 1 to e to the 4th of x over 2 dx. So right off the bat, I know this is an integration by parts problem. One, because x ln of x is a pretty classic example of when to use integration by parts. And then this a minus integral x over 2 thing, this looks a lot like the general formula for when you're doing integration by parts. And I'll show you why in a second. Yeah, so recall that the formula for integration by parts is the integral from a to b of u dv is equal to u times v evaluated from a to b minus the integral from a to b of v du. So this u dv is equal to the original integral, which is this thing here. And then a is the same thing as uv from a to b. And then this integral over here is the same thing as this integral. And so from here, it's just a matter of figuring out what we're going to use for u dv v, and du. And so when you're doing integration by parts, you want to start with finding what you're going to use for u and what you're going to use for dv. And then for u, you're going to differentiate that to find du, and you're going to integrate dv to find v. And so in this example, it's pretty straightforward which things to use for u and dv, because I'm not going to use ln of x for dv, because in order to find v, I'd have to integrate ln of x. And in order to integrate ln of x, you have to do integration by parts. So I'd be doing integration by parts on top of integration by parts. So that's a completely different can of worms that I don't want to open right now. So for here, I'd end up using x by default for dv. And then on the flip side, differentiating ln of x is straightforward. That's just 1 over x. So I'll set u equal to ln of x and dv equal to x dx. So integrating x, that's just x squared over 2. And then the derivative of ln of x is just 1 over x. So now we have all 4 of the things we need to evaluate this and find what a is. And then also, since it's only asking for a, we don't have to evaluate this entire integral. So once we figure out what uv from a to b is, we can just evaluate that and we have our answer. And then if you're a little bit confused about this u dv part, if you plug in u and dv into this, you'll end up with the original integral. So I'm going to focus on this part of the integration by parts formula. So u is ln of x, v is x squared over 2. So this ends up being ln of x times x squared over 2. And our boundaries are 1 and e to the 4th. So a and b ends up being 1 and e to the 4th. And then minus the integral from 1 to e to the 4th of x squared over 2 times 1 over x dx. And when you simplify this, you're going to end up with x over 2. So this ends up being identical to this, like I was mentioning earlier. And so now at this point, it's pretty easy to see how this thing over here is going to be a. So we just have to plug in our boundaries now. So for the upper boundary, you'd have a ln of e to the 4th times e to the 4th squared over 2 minus ln of 1 times 1 squared over 2. And ln of 1 is just 0, so this entire thing simplifies down to 0. And then natural log will cancel out e, so you just end up with the exponent. So ln of e to the 4th is just 4, and then e to the 4th squared is e to the 8th. So this ends up being 4 times e to the 8th over 2, and that simplifies down to 2 times e to the 8th. So now we have a. This is equal to a. And so the answer to this question ends up being C. Number 4. Which one of the following is the most appropriate substitution for the integral of 1 over the square roots of x squared minus 4x plus 13 dx? So this is a trigonometric substitution kind of problem. And I know this just by looking at the answer choices, as well as the fact that you can also see this later down the line. It might not be super apparent at first because we have a quadratic expression here that doesn't look like any of the general forms of when to use a certain trig substitution. But that's because in order to get there, we're going to have to complete the square first. And so to do that, I mean, the goal of completing a square is to come up with a new quadratic expression that factors nicely into 2 duplicates, so you have 2 of the same thing. And so the way I like to do that with completing the square is looking at the b term. So like if this is a, this is b, and this is c, or yeah, ax squared plus bx and c. In this case, b would be equal to -4, a being 1 and c being 13. I like to divide that b term by 2 and then square that. and from there you'll end up completing the square. So I'll do just that. Negative 4 divided by 2 is negative 2, and then negative 2 squared is 4. So our new quadratic expression ends up being x squared minus 4x plus 4. Now we have to figure out how to put this back into the original expression. We can't just put it back in like this because we have a 13 here. And so if we put it back like this, 4 plus 13, you'd end up with 4 plus 13, which is 17, which is not equal to the original expression. So that's just as simple as subtracting 4 from this. So our new expression ends up being this plus 9. And this is equal to the original expression. And then from here, we can factor this new quadratic expression, and we'll end up with x squared minus 2 twice. Not x squared minus 2, excuse me. X minus 2 times x minus 2. And that is the same thing as x minus 2 squared plus 9. And so this ends up being equal to the original expression here. But now this looks a lot more like the general forms of when to use a trig substitution. This would be equal, 9 would be equal to a squared. And then this x minus 2 term is similar to the x squared part. So you'd have x squared plus a squared, the square root of that, and then x squared minus a squared, and then you'd also have a squared minus x squared. And so for this one, we're going to use a tangent substitution. One, because, well, all of the answers only have tangent, but also because of the fact that this is similar to the x squared plus a squared example. In that case, you'd have x be equal to a tangent of theta. Now, the one more thing we do have to do is we need to deal with this negative 2 here, because the substitution says that x is equal to a tangent of theta, not x minus 2. So that is just as simple as moving that minus 2 to the other side of the expression. So we'd have something like x is equal to a tangent of theta plus 2. And then we can find a by just finding the square root of 9, which is 3. So the substitution ends up being x is equal to 3 tangent of theta plus 2. And so the answer to this question ends up being B. And oh yeah, and then also another thing is once you figure out what A is, in this case it's 3, you can automatically eliminate these 3 choices, so C, D, and E, because the A term in these options is 2, not 3. So it narrows it down to A and B. And then from here, this is minus 2, which is not plus 2 like our substitution, so it's down to B. Now, if you're not sure where the substitutions come from, like you might have a hard time memorizing the different scenarios and things like that, there is a way you can derive them manually. And so for this case, I will use the tangent scenario, since that's the substitution we ended up doing. So in order to do that, you'd have to set up a right triangle. And yeah, so you have a right triangle here with your right angle here or something, and then put your theta angle here. And then I will label each side. So the first thing is you have to think about what tangent is actually. And we know that tangent of theta is the ratio of the side opposite to the angle and the hypotenuse over the side adjacent. So for this, I will have x, I'll treat that as the opposite side, and a as the adjacent side. And so you end up with x over a. So tangent of theta is equal to x over a. And then from here, we can figure out where the substitution comes from by using the Pythagorean theorem. So you end up with a squared plus b squared is equal to c squared. And for this, I'm going to replace b with x, since we're working with x and a. So a squared plus x squared is equal to c squared. And then to find c, which is the hypotenuse in this case, c is just equal to the square root. So the square root of a squared plus x squared. And so now we have our hypotenuse here. I'll just label that real quick. And you'll see that this looks like the general form for when to use a tangent substitution. And so basically the way to look at it is when you look at the original problem and you look at this x minus 2 squared plus 9 thing, treat that like the hypotenuse of the right triangle. Or this x squared plus a squared thing, treat that like the hypotenuse of the right triangle. And going back to this tangent theta equals x over a thing, you can see where the a tangent theta substitution comes from by moving things around. So if I just put this down here, we can say that x is equal to a tangent of theta. And now we have the substitution. Number 5. Which one of the following is the correct form of the partial fraction decomposition of 1 over x to the 5th plus 2x cubed plus x? So it's in the question. This is a partial fraction decomposition question or problem. And there are two things you have to do beforehand before you can do the partial fraction decomposition. And the first thing is to check to make sure that the power of the numerator is not equal or greater to the highest power of the denominator. So in the denominator here, the highest power is equal to 5, and the highest power of the numerator is 0 because it's just 1, and any exponent when the exponent is 0, it's 1. So since the numerator's highest power is less than the denominator, we don't have to do an additional step. That would be long division. So say if like this 1 was like a x to the 6th or something, then we'd have to do long division before doing the partial fraction decomposition. And then the next thing we need to do is we need to factor out the denominator as much as we can. We can't come up with a partial fraction decomposition, or at least a meaningful one, right off the bat like this. And so we have to split things up a little bit before we can do anything. And so the first thing I'm going to do in this case, we see that each term has an x term, so we can take out an x. So this is the same thing as 1 over x times x to the 4th plus 2x squared plus 1. So now we have one thing that we can use for decomposition. And now we just have to worry about this thing over here. So x to the 4th plus 2x squared plus 1. And the cool thing is, you may notice this, you might not, but this form, even though it's a quartic expression, it looks very similar to a quadratic expression. And you can do that just by pretending that this 4 is a 2 and this 2 is a 1. And so what I'll do is, to make it easier to see, I'll use a different variable and say like u is equal to x squared. So that would mean that u squared is equal to x to the 4th. So you'd have, so this, using the substitution, you'd have u squared plus 2u plus 1. And then you can factor this pretty easily. You end up with u plus 1 times u plus 1. And since u is equal to x squared, we can just put x squared back into this. So the factored version of this original fraction ends up being 1 over x times x squared plus 1 times x squared plus 1. Now, since we're doing a partial fraction decomposition, another thing you have to realize is we have a duplicate here. This x squared plus 1 and x squared plus 1 is the same thing. So we're going to have to merge this back into 1. So you end up with 1 over x times x squared plus 1 squared. Now, if they were two different expressions, then we can keep them separated and do different things for them. But since they're the same, we have to put them together. And I'll explain why in a second. So the first thing you're going to do is split up this 1 over x term. So for that, since it's just an x, there's no exponents or anything else you have to worry about. It's not a duplicate of anything else. We can just take out an a over x. And now we have to deal with the x squared plus 1 term. And the x squared plus 1, this has an exponent being x squared. And it's also already factored down as much as possible, so we also have to do something to the numerator. We can't just put a b here and then put x squared plus 1 under it. We're also going to have to add an x to the b to account for this x squared term, and then use another letter, so c, and then we can do x squared plus 1. And then similarly, if this term was an x cubed plus 1, then we'd have to use 3 letters. We'd have to do bx squared plus cx plus d or something. So basically the numerator, the amount of letters you'd have to use is equal to the highest power here. So in this case 2. So that's why we use 2. And then with each letter, you need to attach a x to it with an exponent that is 1 lower, if that makes sense. So since this is a 2, it's x cubed, this is just x to the first. And then also, since this is a duplicate, we have to do this twice. With each time we do it, the denominator, the power of it incrementing by 1. So so we'd have a third term, that being dx plus e over x squared plus 1 squared. And so if this was a cubed, then we'd have to do this 3 times. So bx plus c, x squared plus 1, and then again, but with the x squared plus 1 term squared, and then again with the x squared plus 1 term cubed. But since this is only a squared, we only have to do it twice. And so at this point, this is the complete partial fraction decomposition. And so we can pick an answer from here. And so for that, the answer to this question would be D. All right, number 6, evaluate the integral of 5x plus 1 over 2x plus 1 times x minus 1 dx. So this is another partial fraction decomposition question. They're kind of hinting at it because the denominator has already been conveniently factored out for us, so we don't have to worry about splitting it up and trying something. And so yeah, but the cool thing is, for this question, the partial fraction decomposition, or at least the initial setup, is pretty straightforward because both of the terms, there's no exponents or anything. So we don't have to worry about having and there's also no duplicates. So we don't have to worry about anything else other than just splitting this up down to a over 2x plus 1 plus b over x minus 1. Because these terms, the highest power is just 1. It's just an x. And then we can set this equal to the original expression of 5x plus 1 over the denominator thing. So 2x plus 1 over x, times x minus 1. And then from here, now we can solve for a and b to complete this partial fraction decomposition. And so in order to do that, I'm going to multiply each term by the original expression's denominator. So I'm going to multiply this times this 2x plus 1 times x minus 1, as well as this, as well as this. So this will simplify down to a times x minus 1 plus b times 2x plus 1 is equal to 5x plus 1. And now from here, in order to solve for a and b, there are two ways to go about it. And the first thing you'd want to do is you want to start with one of these approaches and then move up to the next one. So for the first one, for the first approach, you can just try by plugging in, think of a number for x and see if you can cancel out something. So in this case, for example, I'm going to start by testing with x is equal to 1, because if I use 1, then I'll be able to cancel out this this a, because it's just a times 0. And then from there, I can just solve for b and find something for b. So I'm going to do that. So when x is equal to 1, you'd end up, a is equal, so when x is equal to 1, you have a times 0 plus b times 2 times 1 is 1 plus 1, so 3, equals 5 times 1, which is 5. I made a mistake. This is supposed to be 2 times 1 is 2 plus 1 is 3. And then 5 times 1 is 5 plus 1 is 6. And so this simplifies down to 3b equals 6. And so from there, b equals 2. So right there we have we have one of our variables, and then from there finding a is pretty straightforward. And then from here, there are two ways you can do that. You can either do the same approach, so using a like a number for x that cancels out b, so that you can find a. Or another thing we can do is, since we have b, we can just plug that in right away for that. Or the third thing we can do is distribute the a's and b's to everything. So you'd end up with an expression that looks like ax minus a plus 2bx plus b is equal to 5x plus 1. And then from there, it's finding the like terms and coming up with equations that relate them. So we have a ax term and a bx term, as well as a 5x term here. So we can say that a plus 2b is equal to 5. And then we can also combine some other like terms. So we have negative a here and b here, and have that equal to 1. And so you'd have b minus a is equal to 1. And then from here, since we know what b is, we can just plug in 2 here. So 2 minus a equals 1. And so a would end up being equal to 1. But for this question, you don't have to do that either. If you want, you can also just plug in 2 right back into this original expression here. Actually, no, you can't. There's some other stuff you'd have to do. So in order to do that. So yeah, this approach works too. And so yeah, so now we have b is equal to 2, and a is equal to 1. And so now we can plug those back into this expression here, and then integrate it, and we'll have an answer. So I will do just that. So our new integral, our split up integral, ends up being equal to the integral of, since a is 1, we have 1 over 2x plus 1 dx plus the integral of 2 over x minus 1 dx. So for this integral, this can be done with a substitution. And for that substitution, I'm going to set u equal to 2x plus 1, so that du is equal to 2 dx, and then dx is equal to du over 2. That should work. And so now this new integral ends up looking like the integral. Oh, and then since this is a definite integral, we don't have to worry about changing the boundaries either. So the new integral ends up looking like 1 over u times du over 2. So that simplifies down to 1 over 2u du. And we also have a constant here, that being 1/2. So we can take that out as well. And from there, the integral becomes obvious. You have 1/2. That's not a good 2. That looks like a z. 1/2 times the integral of 1 over u. And that's pretty trivial. That's just the integral that is just 1/2 times the natural log of u. Absolute value is important here too, when you're integrating a 1 over u kind of thing. And so this integral ends up evaluating to 1/2 times the natural log, absolute value of 2x plus 1. And then for this one, this integral also evaluates to natural log of x minus 1. It might not seem that way at a first glance, but to do that, we can take out a constant, so that being 2. So you have 2 times the integral of 1 over x minus 1 dx. And now the reason this is the integral of this is just 2 times natural log absolute value of x minus 1 is because if you remember, the reason why the derivative of ln of x is equal to 1 over x is because when you're finding the derivative of a natural log, it's actually, let's just say, let's use u again. The derivative of ln of u is equal to u prime over u. So in this case, the derivative of ln of x, the reason why it's equal to 1 over x is because the derivative of x is just 1. And so you end up with 1 over x. So similarly here, the derivative of x minus 1 is just 1. And so that's why the integral of this ends up being ln of x minus 1. So the final solution to this entire thing is 1/2 ln absolute value of 2x plus 1 plus 2 times ln absolute value of x minus 1 plus some constant. So the answer to this question should be, let's see here. We have, I believe, D? Yeah, D matches up with what we had. So yeah, the answer to this question is D. All right, number 7. Evaluate the integral of x times e to the negative x squared from 0 to infinity with respect to x. So this, you may or may not know what integration technique to approach this problem with. So if you're not sure, the thing that I like to do is I have a hierarchy of which technique to start with. So obviously the first one would be the classic reverse power rule. So I guess like power. And then if you can't get it from there, then to use some sort of substitution. And then from there to use integration by parts. And then from there to use a like a trig sub. And then a partial fraction decomposition or something. That's kind of my general hierarchy of what to start with. And so the thing is, for this question, this one you can evaluate this with a u sub, because if you remember, the whole goal with the u sub is to cancel something out to make it like actually integratable. Yeah, it's solvable. Yeah. And so here, it might what thing to use as your substitution is not very. It might not be very apparent at first, but it is there. This might look like an integration by parts question, but it's not. You can try it. You'll see you're gonna not have a fun time. The substitution is super simple, actually. So what you're gonna do is, I'll just say, because no matter what you do, it's not going to be fun. For example, if you try to set dv equal to e to the negative x squared, that's actually impossible using normal integration techniques. You end up with a non-elementary solution. So don't do that. For this, I'm just going to use a substitution. So I'm going to set u equal to negative x squared. So this thing over here, that thing, yeah. And so du would be equal to negative 2x dx. And so dx is equal to du over negative 2x. And so from here, we can plug this back in, but also, since this is a definite integral, we need to adjust the boundaries too, unless you intend on going back to the original variables. But I think it's easier to just adjust them this way. So let's start with the upper boundary, so infinity. Negative infinity squared is just equal to negative infinity, and then negative 0 squared is just 0. So the new boundaries, so the new integral is going to end up looking like the integral from 0 to negative infinity of x e to the u. Oh, and then also a negative here because we have a negative here. So over 2x du. So now the thing that's going to cancel out is right there. You just cancel out these two x's, so you end up with the integral from 0 to negative infinity of negative e to the u over 2. And we know that the integral of e to the u is just going to be e to the u, So that's done right there. So this evaluates to negative e to the u over 2, evaluated from 0 to infinity. So let's handle the upper boundary first again. Since this is an infinity, you'd have to treat it like a limit as u approaches infinity. So you'd have a negative e to the negative infinity power over u. And for this, since it's e to the negative infinity, we can move this e thing down to the denominator. So this equals negative 1 over 2e to the infinity. And this is going to go to 0. So if you have the limit as u approaches infinity of negative 1 over 2e u, if you remember your limits, when you have something like this, since we're going towards positive infinity, e to whatever is going to keep getting bigger and bigger and bigger. So you'll end up with, I don't know, like we can use some big number like 2 billion or something. 1 divided by 2 times e to the 2 billion, you're going to end up with some really tiny number. And the bigger you go, you get closer and closer to 0. So yeah, so this ends up evaluating to this just becomes 0. And then for the lower boundary of just 0, that's just as simple as plugging in 0 for u. So you end up with negative e to the 0 over 2, which just equals negative 1/2. So this integral ends up evaluating to 0 minus negative 1/2, which just equals 1/2. So the answer to this problem is 1/2. Yeah, so the answer to this question is C. Number 8. Evaluate the integral of cosine cubed x from 0 to pi with respect to x. So in this question, we have a trig integral. And the thing with trig integrals like this is the way to approach them is to just try to break it down as much as you can and try to find identities to work with. It's similar to when you're doing a partial fraction decomposition where you have to break down the denominator of the fraction that you're given into smaller parts so that you can have a partial fraction decomposition that you can work with and get somewhere else with. This is no different. Like the first thing you can do with cosine cubed of x is you can split that up. So you'd have so let's write the integral here real quick. You can split this up into the integral from 0 to pi of cosine squared x times cosine of x, and go from there. And right off the bat from here, there's already an identity you can use. If you remember that sine squared of x plus cosine squared of x is equal to 1, then from this identity, you can deduce that cosine squared x is equal to 1 minus sine squared of x, just by moving things around and things like that. And so from there, we're in a really good spot at this point, because now I'm going to swap out this cosine squared x for the 1 minus sine squared x term. So you end up with the integral from 0 to pi of 1 minus sine squared of x times cosine of x dx. And the reason why we're in a really good spot here is because from here it's pretty easy to see what kind of things you can do. Like I'm trying to get to a point where I can do some sort of substitution here. And it's really easy to do that with sine and cosine because the derivatives of them are each other. Like, and so like sine, the derivative of sine is cosine, the derivative of cosine is negative sine, so on and so forth, and it works backwards too, with a couple negatives flipped here and there. So similarly with this, I can do a substitution because I'm going to be trying to cancel out this cosine term here. So for that, I'll just use sine. And even though there's an exponent there, it's not really a problem, because when I set u equal to sine x, this is going to become u squared. And working with u squared is just doing power rule. So I'll continue with the substitution. Du becomes cosine of x dx. So dx is equal to du over cosine of x. And so, yeah, and now we can plug everything in. And then also we have to change our boundaries since we're doing a substitution. So, but here's a cool thing about this question. Just looking at this, I know that this is going to evaluate to 0. The answer to this entire thing is going to be 0. Because you'll see as the original boundaries are 0 and pi. So when you plug 0 and pi into sine x, it'll equal 0. So the new boundaries will become 0 and 0. So the new integral will look like this integral from 0 to 0 of 1 minus u squared times cosine of x du over cosine of x. Now, and then cosine cancels out and you can evaluate it from there, but it's pointless because the boundaries are the same. So the integral is going to be 0. If you're not convinced, I'll do the computation anyway, but this will just end up becoming u minus u cubed over 3 evaluated from 0 to 0. And that's just 0 minus 0 over 3 and so on and so forth. That just simplifies down to 0. So this integral is equal to 0. Yeah, so the answer to this question is going to be E. All right, number 9. Evaluate the integral of 4x times cosine 2x dx from 0 to pi over 4. So straight away, I can tell that for this kind of question, I would want to evaluate this using integration by parts. The reason why is because we have a component here, this 4x, as well as a trigonometric component here. The reason I know I want to do integration by parts here, I'm already in my head, I'm thinking of using 4x as my u. Because if you keep differentiating this, this is going to eventually go to 0 with enough derivatives. So the fact that we have something that's we have an integrand that can be split into 2 parts, one of which we know is going to differentiate to 0 eventually. That's why I'm gonna go with integration by parts for this one. And I'm gonna show you 2 approaches to this, because these kind of questions, there is a different way of doing integration by parts that will also save you a ton of time. So I'll do it the normal way first. So we know that the formula would be the integral from a to b of u dv is equal to uv evaluated from a to b minus the integral from a to b of v du. So this u dv integral would be equal to the original integral. And now I'm going to find a u and I'm going to find a dv. Oh, wait, let me move this a little bit. So in situations like this, when you have 2 parts that both of which can be integrated or differentiated pretty easily, try to see if you can find one that will eventually differentiate to 0. So in this case, we know that 4x is eventually going to go to 0 because the derivative of 4x is 4 and the derivative of 4 is 0. So for u, I'm going to use 4x, and so du ends up being 4 dx. And then for dv, I'm going to use cosine of 2x and then integrate that to get v. Can't forget the dx there. And you end up with sine of 2x over 2. And so now we have our first round of things we can do. Also, another thing, it's very important. I haven't mentioned it before, but when you're integrating a definite integral by parts, every time you create a uv term like this, you have to plug in the boundaries of the integral into it and evaluate those uv parts individually, which is a little different from other integration techniques, but that's very important. There are situations where you can end up with a different answer if you wait until the very end to plug in the boundaries. So yeah, that's very important. So let's plug in what we have. So u du v dv, and we'll have a 4x times sine of 2x over 2, evaluated from 0 to pi over 4. and then minus the integral from 0 to pi over 4 of sine of 2x over 2 times 4 dx. And so from here, the cool thing is we only have to do integration by parts once, because this second integral, we can just evaluate it as is. So I'm going to do that. First, let me simplify this entire thing, and then I'll do just that. So this simplifies down to 2x times sine of 2x evaluated from 0 to pi over 4 minus 2. We can also take out a constant here, because 4 divided by 2 is 2, and 2 is a constant, so I'll take that out of the integral as well. So you have 2 times the integral of pi over 4 the integral of sine 2x dx. And then the integral of this is just this equals negative cosine. And so I'm going to flip this too, because this is a minus. So we end up with 2 times cosine of 2x over 2. So these 2's will cancel out. So this just ends up being cosine of 2x evaluated from 0 to pi over 4. And then also have to evaluate this from 0 to pi over 4. So when we plug in the boundaries, you end up with 2 times pi over 4 sine of 2 times pi over 4 minus this, but with 0. But I'll start with this. So we end up with pi over 2. This simplifies to pi over 2. And this also simplifies to pi over 2. And sine of pi over 2 is just 1. So this just simplifies to pi over 2. And for the second part, for 0, 2 times 0 is 0, so this entire thing is going to become 0. So we know that this entire thing simplifies down to just pi over 2. And then for this, we have cosine of 2 times pi over 4 minus cosine of 0. And this becomes cosine of pi over 2, which is 0, and minus cosine of 0, which is 1. So this simplifies to negative 1. So the answer to this integral, to this entire problem, ends up being pi over 2 minus 1. And if we look at these answers, the closest thing to that would be A, which is just, it's the same thing, but slightly different, where the 1 is just, they turned this 1 into a 2 over 2, so you'd have like pi over 2 minus 2 over 2, which simplifies to pi minus 2 over 2. So the answer to this question is A. Now, I'm going to show you a different way to do this. And I would highly recommend practicing this integration by parts technique, especially if you need to take differential equations or something. It'll come in handy because you'll be doing integration by parts a lot for when you're taking a differential equations course. So here, I guess that would be MA 266. So instead of using this formula, we're gonna make a table, and the name of this method is called tabular integration. So the first thing we're gonna start with is we're gonna make a table with 3 columns. One for your sines, so S, one for your derivatives, so D, and then one for your integrals, I. And for sines, that's just plus or minus. And we're going to go down one by one, so we're going to start with plus. Every time you do this method, you want to start with plus. For D and I, derivatives and integrals, the process of choosing, you do the same process as the regular way of doing integration by parts, of picking a u and a dv. And whatever you pick for your u, you put that in your derivatives column. And whatever you put for dv, you put that in your integral column. So we're going to use the same u and dv that we used in the original computation. So I'm going to put 4x here, and I'm going to put cosine of 2x here. And now we're going to go down one by one, and with each pass, the signs are going to alternate. So the second time, now it's going to be negative, and then we're going to differentiate 4x. So the derivative of 4x is 4, and the integral of cosine of 2x is sine of 2x divided by 2. And then we do it again and flip the sign again, so now it's positive, and the derivative of 4 is 0. And then the integral of sine of 2x over 2 is negative cosine of 2x over 4. And basically, the way you know when to stop doing this is when your derivative column reaches 0. And so usually when you have a question like this where you have a part that you know will differentiate to 0, chances are you can probably save a little bit of time doing the tabular method like this. So now that we had the derivative reach 0, now we're going to multiply diagonally like this. So we're going to multiply 4x by this sine 2x over 2 term, and we're going to multiply 4 with this negative cosine 2x over 4 term. And then also don't forget these signs. And with each product that you create, you need to evaluate the boundaries at it with each pass, similar to the normal way of doing it. So you'd end up with positive 4x sine of 2x over 2, evaluated from 0 to pi over 4. And then here we have a negative here and a negative here, so it becomes positive. So you end up with plus 4 times cosine of 2x over 4. And you'll find that when you simplify this down, you end up with the same result as the previous form. Oh, also, yeah, and then evaluate this from 0 to pi over 4. And so when you evaluate this entire thing, you're going to end up with the same result of, let me find it. You're going to end up with this thing, this pi over 2 minus 1 thing. So it's just a neat little trick. It's especially useful for these kinds of integrals. Now you can use the tabular method for any sort of integral with that requires you to do integration by parts. It's just a little bit trickier and it takes a little more finesse. But for these kind of integrals, and so I would probably suggest sticking to the regular method for any other sort of integration by parts problem. But for any kind of integration by parts problem, where you have a part that differentiates to 0 eventually, this method will save you a ton of time. All right, number 10. If 1 over x squared times x minus 1 squared is equal to a over x plus b over x squared plus c over x minus 1 plus d over x minus 1 squared, then what is the value of a plus b plus c plus d? So this is another partial fraction decomposition question. And unlike the previous, there's another partial fraction decomposition question on this exam that focused on the actual decomposition. This one is focusing more on figuring out what the a, b, c, and d terms are. And they've already conveniently done the decomposition, the initial decomposition for us, so that saves us a little bit of time. So what I'm going to do for this is I'm going to multiply both sides of this equation by the denominator of the original equation. So that would be this. So the denominator being, in this case, I'll use x squared times x minus 1 squared. So when you multiply that out, you end up with x squared times x minus 1 squared times a over x plus b over x squared plus c x minus 1 plus d x minus 1 squared. And when you multiply that out, you end up with a times x minus 1 squared plus b times x minus 1 squared plus c times x minus 1. No, x squared times x minus 1. And then plus d x squared. Now I am going to figure out what x minus 1 squared is because that's going to be important for the future. So that would be x minus 1 times x minus 1 is equal to x squared minus 2x plus 1. We're going to use that for later. But for now, oh yeah, and then also this entire thing is equal to 1 because we multiplied this entire thing by this denominator. So that it would cancel out and you'd end up with just 1. So from here, whenever you're trying to find what these letter terms are, it's always good once you have this equation to try to just plug in test numbers for x and see if you can't set other things to 0 to isolate certain variables and try to figure them out. So in this case, I'm going to start with x is equal to 1, because if I do that, I can get rid of a, b, and c and figure out what d is right off the bat, because x minus 1 is 0. So this thing becomes 0, this also becomes 0, and then this also becomes 0, plus d times 1, because 1 squared is 1, equals 1. So we know that d is equal to 1. That's one letter out of the way right away. So the next number I'm going to try, because we can also use 0. We can set x equal to 0. And what that'll do for us is that'll isolate b and get rid of a and c, because there's a x here, so it multiplies the entire thing by 0. So you end up with 0 plus b, because 0 minus 1 is -1, but you square that so it becomes positive. So you end up with b plus 0 again, plus 0, because d times 0 is 0. And again, we figured out what b is just by eliminating everything else. So b is also equal to 1. So that's 2 letters out of the way. Now at this point, there isn't really any other numbers you can test with. So at this point, I'd multiply everything out and go from there. So I'll do just that. You can so this is where me multiplying this out, foiling this earlier comes into play. This becomes a x cubed minus 2x squared plus x plus b times x squared minus 2x plus 1 plus c x cubed minus x squared plus dx squared is equal to 1. So from here, now that I have this new equation, I'm going to relate like terms together on both the left side and the right side. So x cubed terms, x squared terms, x squared terms and x terms, and then also no variable terms. And since the right side only has a 1, I know that what is it? Any x cubed terms, x squared terms, and x terms, they're going to add up to 0. So here I'll start with we have an ax cubed term and a cx cubed term. So a plus c would be equal to 0 because there's no x cubed term here. If there's something like a 5x cubed here or something, then a plus c would be equal to 5. And so then I'm going to do the same thing, but for the x cubed term. So we end up with negative 2a plus b minus c plus d is equal to 0 as well, because there's no x cubed term on the other side. And then I'm going to do the same thing for the x terms. So we end up with a minus 2b equals 0, because there's no x term on the other side. And then the cool thing about this one is we can find out a from this because we know what b is. We know that b is equal to 1, so we end up with a minus 2 is equal to 0, so we know that a equals 2. And if you want, since we have 3 of the letters, we can just plug them all into this a plus, or we just plug it into this a plus c is equal to 0. Since we know that a is equal to 2, we put 2 plus c is equal to 0. We just know that c equals negative 2. So now we have all 4 of the letters. We know that d and b are equal to 1, a is equal to 2, and c is equal to negative 2. So a plus b plus c plus d is equal to 2 plus 1 minus 2 plus 1, which just equals 2. So a plus b plus c plus d is equal to 2. So the answer to this question is D. Number 11, evaluate the integral of x squared times e to the x dx from negative infinity to 0. So I know right off the bat that this is an integration by parts type of integral, because we have a part here that is going to differentiate to 0 with enough derivatives, while integrating or differentiating e to the x is going to stay the same. So that makes our job a little easier when it comes to figuring out what things we're going to pick for differentiating and integrating. And similarly, since this type of integral, since this x squared term will eventually differentiate to 0, there are two different ways we can solve this effectively by using the normal way of doing things. So using the formula of from the integral from a to b of u dv is equal to uv from a to b minus the integral from a to b of v du. And so we'll start by picking a u and a dv. So for u, I'm going to use x squared, and then I'll differentiate that and you end up with 2x dx. And then for dv, I'm going to use e to the x, and v is also e to the x, since we just integrated e to the x. And this is nice because we're integrating something that's always going to stay the same, while this derivative is going to keep going closer and closer to 0. X squared, 2x, 2, and then 0. And now that we have our u, du, v, and dv, we can plug everything in to the original integration by parts formula and evaluate from there. And since this is a definite integral, we're going to have to plug in the boundaries of u and v of these every time. We're going to have to plug in the boundaries individually every time we come up with a uv term like this. So I'm going to start the first pass, so you end up with x squared times e to the x, evaluated from negative infinity to 0, minus the integral from negative infinity to 0 of e to the x times 2x dx. So once again, for this integral, we're going to have to integrate this by parts again, so come up with a new u and dv. But for this one, we're going to use the same process because we still have something that's going to differentiate to 0. So dv is going to remain as e to the x. So if we do u sub 2, we're going to set that equal to 2x, and we're going to find that du sub 2 is equal to 2 dx, and then dv sub 2 is equal to e to the x. So v sub 2 is also equal to e to the x. So we're going to do the same thing. So our new integral is going to end up looking like x squared e to the x from negative infinity to 0 minus, I'm going to use brackets here since this is a new integral. We're going to use the same formula as before, where we have 2x times e to the x evaluated from negative infinity to 0 minus the integral of 2e to the x dx from negative infinity to 0. Now this integral, it's going to become 2e to the x, and then we can plug in the boundaries here. So now we have we've integrated the entire thing, and so that ends up looking like e to the x from 0 to negative infinity minus 2x e to the x evaluated from negative infinity to 0 plus, because we have a minus here and a minus here, so they're going to flip each other. So you end up with a plus here, 2e to the x evaluated from negative infinity to 0. So interestingly, this seems really tedious because you have to do a couple limits for each of these. But recall what I mentioned earlier. I'm going to keep going back to the fact that x squared differentiates itself eventually to 0 with enough derivatives. That's very crucial for this part of how to take a little bit of a shortcut. You don't have to evaluate these limits individually and stuff because you'll see. I'll start with this one, and you'll see what I mean. So first off, the upper boundary is 0, so we know that it's going to evaluate to 0 at the upper boundary. So you end up with 0 minus x squared times e to the negative infinity, which I'm going to move to the bottom so that it becomes e to the positive infinity. So for this, the limit of this, to find the limit of this, you can use L'Hopital's rule, because when you plug in infinity for both of these, it becomes infinity over infinity. And so if you do L'Hopital's rules twice, you'll start with x squared over e to the x, and then that becomes 2x over e to the x. And then the second time it's going to become 2 over e to the x. But the difference is, but this limit is also going to evaluate to 0, because once you get to this point, you end up with 2 over infinity. And this is a bottom heavy fraction. So as infinity gets bigger and bigger, it's going to become smaller and smaller. So when you have like 2 over 9,000 or something, it's going to be 0.0001 or whatever. And it's going to get closer and closer to 0. So this first portion ends up being 0 minus 0, which is just 0. And then the same process applies to this second portion. This second portion is also going to be 0 minus 0. The reason being, for the upper boundary, it's going to end up being 0. And then for the lower boundary, same thing, except if we're going to start from this, instead. When you apply L'Hopital's rule, you end up back here with the same 2 over infinity thing. So that also evaluates to 0. So you end up with 0 minus 0 again. So 0 minus 0 minus 0 minus 0 is just 0. The difference with this one is we start with, for this one, we start with 2 instead of 2x or x squared. So when we plug in the upper boundary, it's not going to be 0. It's actually going to be 2, because e to the 0 is 1, and 1 times 2 is 2. So you end up with 2 minus 0, because when you plug in the lower boundary, you end up with the same result as the previous 2 passes. So the answer to this integral ends up just being equal to 2. So the answer to this question is going to be B. Now, if you saw my explanation on another integral on this exam that was also evaluated using integration by parts, that integral also had a part that eventually differentiated to 0. And so another way you can do this kind of problem is you can use a little thing called tabular integration. And what you'll do is you'll set up a table again. So where did my marker go? Here it is. With 3 columns. So you'll have sines, derivatives, and integrals. So S for sine, derivative D, I, integral. And you're going to start with a plus. And for the derivative and integral columns, it's the process of picking what part you're going to put into each of these these columns is the same process as when you're picking a u and a dv for when you're doing integration by parts normally. So I'm going to use the same original u and dv that I used for the original problem. So I'm going to use x squared in my derivative column, and I'm going to use e to the x in my integral column. And then we're going to go down another row and flip the sign to minus. And then with each pass, you're going to differentiate the derivative column and integrate the integral column. So the derivative of x squared becomes 2x, and then the integral of e to the x just stays e to the x. And then you're going to do another pass and flip the sign back to positive. Differentiate again, you end up with 2. And then you integrate this, you end up with e to the x again. And you're going to keep doing this until your derivative column reaches 0. And so we've reached 0 here, while this remains e to the x. So now at this point, now all we have to do is multiply diagonally like this, and while accounting for the positives and negatives. And with each product that we create, you have to evaluate the boundaries. You have to plug in the boundaries at each product that you create. So we'll end up with x squared times e to the x, evaluated from negative infinity to 0. And then we end up with this again. So you end up with minus 2x e to the x, evaluated from negative infinity to 0, plus 2 times e to the x, evaluated from negative infinity to 0. And what you'll see is this result is identical to the results that we got over here. And so it's just the same process from here of plugging in the boundaries, and you'll end up with the same result of this entire thing will end up equaling 2. All right, number 12. Evaluate the integral of 1 over x times the square root of 4x squared minus 1 dx. So right off the bat, this integral, it's going to be a trig substitution integral. You can kind of tell by looking at this square root over here, this 4x squared minus 1 portion. If you look at it closely, this is leading towards some sort of secant substitution. And I know this because if you recall what the general forms are of a square root for when you're trying to do a trig substitution, we know that x squared minus a squared, when you see something like this, then you're going to want to do a secant substitution, that being x equals a secant of theta. If you see a squared minus x squared term, that's when you're going to want to do a x equals a sine of theta kind of substitution. And then lastly, if you see an x squared plus a squared term within a radical like this, then you'd use a substitution setting x equal to a tangent of theta. Now, if you don't want to remember this, or you can't, or you're not, and you're still not sure, you can derive these substitutions manually. And for this example, since we're going to be using a secant substitution, I will do so. I will show an example of how to derive the secant substitution manually. So what you're going to want to do is you're going to want to set up a right triangle like this with angle theta in the right side over here, or the top, it doesn't really matter. What does matter though is what you label each side. So recall that cosine of theta is, that's an ugly S. Cosine of theta is the ratio of the side adjacent to the hypotenuse over the hypotenuse, so A over H. And we know that secant of theta is equal to 1 over cosine of theta, so that's equal to the ratio of the hypotenuse over the adjacent side, so the reciprocal. And so with that in mind, we can use this alongside the Pythagorean theorem to kind of connect the dots on where the substitution comes from. So for this one, I'll start from here, and let me just get rid of this 1 over cosine theta thing here, and just say hypotenuse over adjacent. And from here, I can just move the a over to this side, so we end up with a secant of theta is equal to h. So for this example, I am going to label the hypotenuse as x, and I'm going to label the adjacent side as a. And the reason I'm doing that is because in these general forms, we're using the variables x and a. And so now we're going to bring this up with the Pythagorean theorem. So a squared plus b squared is equal to c squared, where c is going to be the hypotenuse. And since we labeled the hypotenuse as x, I'm going to replace c with x. So now it's going to look like a squared plus b squared equals x squared. And from here, we can solve for b to find what the length of this side is going to be. And once we find the length of this side is going to be, you're going to find that it's going to look like this form. Because when we solve for b, we're going to get that b is equal to the square root of a squared, the square root of x squared minus a squared. And so now we know that the length of this side is going to be the square root of x squared minus a squared. And then we also know that since x is the hypotenuse, we can also replace h with x here. And from here, if you treat this, going back to the original problem, if you treat this radical like this side over here, it's kind of easier to see where the substitution comes from. And so yeah, so that's how you derive the secant substitution manually. So now from here, I'm going to start focusing on setting up the actual substitution for this integral. So for this, since we know that x is going to be equal to a secant of theta, we're going to have to figure out what a is going to be. And so in order to do that, the way I would do it with this integral is first I would isolate this 4. And the way I'm gonna split it, I'm gonna split this into 2 radicals. So this is going to become the integral from 1/2 to 1 of 1 over x times the square root of 4 times x squared minus 1/4. And so from here, now it's a little easier to see what a is going to be. If we say that a squared is equal to 1/4, then a would be equal to 1/2. So now we have our substitution. X is going to be equal to 1/2 secant of theta. And since this is a substitution, the general process from here is going to be the same as a u substitution. Pretty much the only difference being the thing we're using for a substitution is different. But we also need to set up a dx, so the derivative of this x. So that would be equal to 1/2 secant theta times tangent of theta d theta. And another thing we're going to have to do is we also need to adjust the boundaries since this is a definite integral. And so in order to do that, the way I like to look at the integral symbol with the boundaries when it comes to a trig substitution is instead of looking at it as just 1/2 and 1, it makes more sense if you look at it as like this, where you have x is equal to 1/2 and x is equal to 1 here, because that's what it is. That's what the boundaries are basically. It's like if you were to integrate this as is and plug in these boundaries, like, oh, what is it when x is equal to 1/2 and what is it when x is equal to 1? And so since for this substitution, we're integrating with respect to theta, we have to set this up in such a way where we have like theta is equal to what and theta is equal to what here. And so that's what I'm going to do here. And the way I'm going to do that is, since we know that our original boundaries are 1/2 and 1, I'm going to say that first I'm going to set x equal to 1/2. So let's say that 1/2 is equal to 1/2 secant of theta. So from here, the 1/2s and the 1/2, they're going to cancel out. So we can say that 1 is equal to secant of theta. So theta is going to be equal to the secant inverse of 1. And then we can do the same thing for the upper boundary and say that 1 is equal to 1/2 secant of theta. And from here, we can deduce that theta is going to be equal to the secant inverse of 2. So now we have everything and we can start computing the integral from here. We have the substitution, we have the derivative of our substitution, and we have our new boundaries. So the new integral is going to look like this. So we have the secant inverse of 1 at the lower boundary and the secant inverse of 2 as the upper boundary. And I'm going to replace, I forgot a dx there, by the way. I'm going to replace dx with our new dx being 1/2 secant theta times tangent theta. So the numerator is going to look like 1/2 secant theta tangent theta d theta over, and then since like a u sub, we're going to replace x, wherever we see an x, we're going to replace it with our substitution. So I'm going to replace all the x's with 1/2 secant theta. So it's going to look like, I'm also going to simplify this square root of 4. I'm going to turn that into a 2 now. And you'll see why in a second. So when we plug in all our x's, the integral is going to look like 1/2 secant of theta times 2 times the square root of, since this is an x squared, this is going to become 1/4 secant squared theta minus 1/4. So I know at a first glance this looks horrible, But at the same time, you're going to see that a lot of this stuff is going to cancel out, and it's really not as bad as it looks. Like first off, we can see there's two 1/2s here, so these are going to cancel. And then there's also two secant thetas here, so these are also going to cancel. So now our new integral looks like this, where we have boundaries again now the integral is going to look like tangent theta d theta over 2 times the square root of 1/4 secant squared theta minus 1/4. And then the next thing we can do from here is we can take out a square root 1/4. And so when we do that, this integral is going to look like this. So we have and then I'll put the boundaries back later just to save space. I'm just going to write the integral like this. We have tangent d theta, and we end up with 2 times the square root of 1/4 times secant squared theta minus 1. And just like when I took out the square root of 4 over here, I can do the same thing here. The square root of 1/4, that just becomes 1/2 and cancels with this 2. So now all we have left is this 1 times secant squared theta minus 1. And now you can probably see just how simple this integral actually is, because if you recall, this is an identity. Secant squared theta minus 1 is an identity, that being equal to tangent squared of theta. So this is going to become tangent theta over the square root of tangent squared theta. And the square root, oh, and then a d theta there. And then the square root of tangent squared theta is just tangent theta. And so that cancels with this tangent theta. So this entire thing reduces down to the integral from secant inverse of 1 to the secant inverse of 2, 1 d theta. And that's pretty easy. The integral of 1 is just theta. So this entire thing just ends up becoming theta evaluated from secant inverse of 1 to the secant inverse of 2. Now also, these boundaries are also not as bad as they look. At a first glance, it might look a little scary, but when you I'm going to relate this to cosine, and it's going to make more sense. So we know that secant of theta is equal to 1 over cosine of theta. And so on the flip side, the secant inverse of theta is equal to the cosine inverse of 1 over theta. So with this in mind, we can rewrite these boundaries and plug them in as, instead of as just secant inverse, we could plug it in as the cosine inverse of 1/2 minus the cosine inverse of 1, since the inverse of 1 is just 1. And so from here, it's a lot easier to see where I'm going with this. Now you just have to figure out this is going to evaluate to pi over 3, because cosine of pi over 3 is 1/2. And then this is going to evaluate to 0, because the cosine cosine of 0 is 1. So this just equals pi over 3 minus 0. So our final answer for this entire thing is just pi over 3. So the answer to this question is going to end up being B.